Hi, my name is Manish Gupta, and in this video, I'm going to talk about our recent work called OAK, which involves enriching document representations using auxiliary knowledge for extreme classification. This work is in collaboration with Shikhar, Deepak, Anshul, Sayak, Bhawna, Jian, and Manik, all from Microsoft. This is going to be presented at ICML this year. So let's get started. Okay. What is extreme classification? And I'll also talk about what was missing in previous extreme classification methods. So extreme classification is this field of machine learning, which involves predicting the most relevant subset of labels for a data point from an extremely large set of labels. So for applications like product recommendation, document tagging, search and advertising, query recommendations, typically you have a multi-class classification problem where there are millions of classes and you want to choose, it's a multi-label multi-class classification problem, which means you have to choose a small subset of labels that are relevant from this large, extremely large set of labels. And that is what is called the extreme classification. Okay. Um, in typical extreme classification scenarios, the input could be very short or could be very long. Okay. However, for several applications like in search and ads, the input is actually very short. So for example, user queries and product or web page titles are actually very, very short in size. But you do want to actually do extreme classification on them. For example, you may want to map queries to keywords in an ads application. In a recommendation application, you may want to map products to related products. In a Wikipedia to category mapping kind of application, you may want to map the title, the web page title to a Wikipedia category, right? So in all of these cases, the sparse representation of these short text extreme classification data sets is bad. Okay. For example, in a popular extreme classification benchmark dataset, wiki titles 500K, the input text is just 3 to 5 words. Okay. Now, in these cases, extreme classification methods often suffer from this sparsity in the representation. Interestingly, these data sets also have relevant auxiliary information which is available from other sources. For example, there could be frequently clicked web pages for search queries in sponsored search, while the main extreme classification problem is to map a query to a bunch of keywords. You could also use frequently clicked web pages as an extra auxiliary information so as to improve the main extreme classification task. Similarly, if you consider the extreme classification task of query autocompletion, that is mapping a prefix to a suffix, you could basically take previously searched queries for web search as an extra context or extra auxiliary information so as to solve this main task of mapping prefix to suffix. In this example that is shown at the bottom, the main task is to take a Wikipedia article and find other related Wikipedia pages, also called as the see also task, right? Here, the auxiliary information that could be used is all relevant categories associated with the Wikipedia page title. So as you see, the Wikipedia page title is plinth assemblage. And here are the relevant categories associated with this particular Wikipedia document or Wikipedia page title. Right? Now, if you notice, this is the standard endgame, the state-of-the-art extreme classification method, which does not use any auxiliary information. It actually incorrectly predicts some of these other see also Wikipedia page titles. Okay. On the other hand, OAK, which is our method that I'll talk about in the next few slides, uses auxiliary information and therefore is able to predict all good ones, all good labels. The black ones are all good labels anyway. Green ones are those labels which are also good, right? But red ones are the ones that are bad. Right? So OAK basically using auxiliary information is actually able to predict better results. Okay. So how do you use these auxiliary knowledge pieces? If you have auxiliary information, that's great, but how do you make use of that, right? So the idea is given a document X, first you have to actually discover those auxiliary knowledge pieces that are related to the document X, right? So the broad goal is that you must build some module to actually discover K auxiliary knowledge pieces. Right? So, and you could do that using standard retrieval augmentation methods that are very popular in the realm or RAG literature these days. Right? And using that, there are two naive approaches that I'll talk about on this slide. The first approach basically just says concatenate the string representation for the input document X with the string representation of the auxiliary knowledge pieces, and then pass it through the document through some encoder like a BERT encoder so as to get a full extended document representation. Okay. Now, there are some problems with this approach. One, the accuracy may suffer if some auxiliary knowledge pieces are noisy, right? So basically, auxiliary knowledge pieces, basically, if they are linked using some predictive method, there could be noise, right? And accuracy may suffer, right? Second, inference latency may increase due to the increased length of input. As you know, most of these encoders are transformer-based these days, and transformer methods suffer from the quadratic complexity of computation, and therefore inference latency may actually increase as you increase the length of the input. Okay. So another approach is to basically use graph neural network methods. So using graph neural networks like graph formers and graph sage, which are popular graph neural network based methods for extreme classification, you could try to encode the document to auxiliary knowledge pieces linkage information. Okay. However, there are problems with this as well. The first being high storage and computation costs, right? And second, it cannot leverage the auxiliary data sourced from these disparate tasks effectively, okay, as we will see in the experiments as well. Okay. So therefore, in this paper, we propose OAK. OAK is online auxiliary knowledge. Okay? And here is the OAK's broad architecture. I'll go over it in the next few slides. Right? OAK follows three-stage training. OAK basically contains several blocks that you see here. For example, here is linker. So essentially, you start from the document DI. So that's your input. Okay. And you want to find out if label LJ is relevant to the document DI or not. Okay. So you start with the document DI, you essentially pass the document through an encoder, you get an encoder representation. So this encoder could be any BERT-based encoder or transformer-based encoder, right? So you get this encoder representation. You actually also pass the document through a linker. Linker basically gives you the top K documents. The linker R gives you the top K documents that are relevant to the input, top K auxiliary knowledge pieces that are relevant to your document DI. And then, for each of those auxiliary knowledge pieces, you have a vector representation in the auxiliary knowledge bank. From that bank, you basically figure out for these top K, the relevant knowledge pieces, the vector representation for the relevant knowledge pieces, and then you combine. So you're not combining at the input string level, but you're actually combining the embedding for the input document with the embedding for these auxiliary knowledge pieces. After you combine these embeddings, essentially you try to, of course, on the other side. So this is basically called as the augmentation block. The augmentation block augments, combines everything, the input document, and essentially your auxiliary knowledge pieces, their representation, and gives you a overall representation called phi. Right? Now, you also have the same encoder that was used for encoding your document to encode the labels as well. And when you encode those labels, you basically get an encoder vector for the label. You take this encoder vector for the label, yj, and you take this x hat, right? And then you try to, optimize for a Siamese loss to train the encoder. And of course, you can also train the classifier here by optimizing for the similar kind of a Siamese loss, but this time also bringing in the extreme classification classifiers. Okay, so this part is basically just the same as endgame. So if you have not looked at endgame, I really motivate you to look at the endgame video to be able to understand and appreciate this part. Right. Overall, the output score that you obtain is basically a combination of the encoder optimization score and the classifier score, right? So the overall score is obtained as a fusion of the encoder and the classifier scores. Okay, I'll get into those details one by one. So overall, OAK training actually involves three stages: the linker training, OAK pre-training, and OAK fine-tuning. Okay, the linker training basically just involves training this guy, so the linker guy. And this is not done in a joint manner. It's a separate stage training. So you link documents with relevant AKPs or auxiliary knowledge pieces using an XC method. So it's trained separately to basically be able to link a document to auxiliary knowledge pieces using some extreme classification method. You could just use Endgame for that matter. Okay. OAK pre-training actually involves training the augmentation block. So when I say OAK pre-training, I'm actually, I actually mean pre-training this augmentation block, which is highlighted with this background color. Okay. And it is basically trained in a Siamese fashion using triplet loss, which I'll detail in the next few slides. Of course, the augmentation block, while doing a pre-training, sort of uses the combiner to combine the document embeddings with the relevant trainable AKP embedding. So these vector representations for those AKPs in the auxiliary knowledge bank are all trainable. Okay, you start with the random initialization and you train them over time. Now, this combiner is just not simply concatenating the document with those representations, but it actually does that in an attention-based pooling manner. Okay, and again, we'll talk about details later. Okay. Now, while doing oak pre-training, you want to ensure that there is good encoder regularization. So as to ensure that these representations are not very far away from the representations that you have trained using just the encoder. Okay. Also, we use a special kind of calibration loss, which is inspired by a recent DPO paper. DPO stands for direct preference optimization, and in some ways, it's sort of a replacement for standard RLHF methods. Okay. Okay, so that's that. So in some ways, augmentation block is basically pre-trained using oak pre-training stage. Okay. Once you're done with that, what we do is to do oak fine-tuning, which is where these classifiers are going to be trained. So for oak fine-tuning, we freeze the augmentation block parameters. So this highlighted block is all frozen, all the parameters are frozen, and you learn this guy, delta WJs. Okay. So that you can actually finally get the overall classifiers per label, WJ for j equal to 1 to the label set size. Okay. So you learn a per vector, per label, you learn a per label refinement vector being this delta WJ to fine tune the label embeddings to obtain the final label classifiers WJ. Okay. Let's get into details. So you see the encoder guy here. So we'll sort of represent that using E, and that sort of tries to figure out a representation, a d-dimensional representation for the input document X with trainable parameters theta E. So of course, this could be some BERT-based model like distal BERT-base. So start with the pre-trained distal BERT-base, but you fine-tune it so as to basically get trainable, so as to get those parameters theta E. Okay. There's a linker R as well, right? And its job is to basically take the input document and return, k relevant AKPs from the overall set of possible AKPs. Okay, it has its own parameters theta L. Okay, and then there is auxiliary knowledge bank, this guy, right? So which basically contains, of course, if they are totally A knowledge pieces, it size of A knowledge pieces, it basically contains an embedding for each of them. So, and then there is going to be a combiner module, which basically will have its own parameters theta C for attention-based combination. Okay. So overall, you have like a theta E in the encoder, parameters to be trained, theta K in the in the linker. In that sense, is the parameters to be trained there, and then theta K, being the parameters to be trained for auxiliary knowledge bank. And then you have the parameters theta C to be trained for the combiner. Remember that linker is already trained in the first stage, right? So that's that. So you basically, in the oak pre-training stage, that is what you end up pre-training or, training, okay? So overall, once you're done with all of that, the combiner guy basically combines your input document along with the K knowledge pieces, their representations, in an attention-based manner, so as to give you the enhanced representation for the document. Okay. Now, as I was talking about the three-stage training, linker training is a standard training using any extreme classification model. The oak pre-training part basically focuses on maximizing mutual information in two ways: between this enriched representation phi and the label representation here. So that's one way. The second thing it also does is to make sure that it basically maximizes the mutual information between the encoder representation and this label representation. Remember, encoder regularization needs to be done. Even if you add a whole bunch of these auxiliary information, these guys, phi and encoder representation should not differ by too much. And therefore, what you want to do is to maximize mutual information between both, phi and, encoded representation from the label side and, the encoded representation from the label side and the document side. Okay. Now, to keep notation simple, we could sort of represent this phi notation with xi hat and the label representation by y. It's on the y side in some ways, and the encoded representation for the document by xi itself. Okay, so xi hat is sort of a revised version of xi with the metadata or the auxiliary knowledge information included. Okay. So that's that. Now, maximizing mutual information is equivalent to minimizing the triplet loss. The proof is there in the paper, but I'll not go over it. Okay, so you can look at the paper to understand the proof. Okay, so therefore, what we do is to essentially try and maximize and minimize the triplet loss for both of those scenarios: the scenario where we use phi and the scenario where we use the encoded representation for the document. Okay, so of course, when we use phi, we are going to use xi hat because that's basically the rich representation of the document enhanced by the auxiliary knowledge pieces. And when we use, the encoder representation, we are basically just going to use the original encoder representation for the document XI. Okay. Of course, you want to actually do triplet loss by maximizing the similarity with the relevant label and minimizing the similarity with a non-relevant label by a margin gamma. Okay. So that's that. Now, so therefore, overall loss is basically the triplet loss for the enhanced representation plus the triplet loss for the encoder representation for the document. Okay. Now that's that. So we have done this maximization of MI, but that's not enough. Okay. So that's not enough, and we actually do one more step of doing mutual information calibration. Okay. Now, the idea is as follows. When you look at why, ideally, since it is enhanced by this information from auxiliary knowledge pieces, it should have more information that can predict accurate labels compared to this guy. Okay. So therefore, what we want to do is to ensure that when DI and LJ are relevant to each other, the similarity between DI and LJ's representation, phi and LJ should be higher than the similarity between this encoded representations of document and LJ. Okay. So what we want to do is as follows. We want to compute the confidence difference. How much the model is more confident thanks to coming up with a AKP or auxiliary knowledge piece enhanced representation for the document. Okay. So when delta ij is +1, that is when di is and lj, the document di and label lj are relevant. You want to ensure that the similarity between this guy 1 and this guy 2 is higher than the similarity between 2 and 3, between 2 and 3. Okay, so that's basically what is encoded in this MI calibration loss. And overall, then the OAK pre-training stage essentially makes use of these two losses, or actually if you factor this into two further losses, it's basically optimizing for these three losses. The triplet loss between 1 and 2, triplet loss between 3 and 2, and then, calibration loss computed over 1, 2, 3. Okay. So that's that. Now, of course, you also need to do OAK fine-tuning. So once you have done the OAK pre-training, what we do is to essentially freeze the parameters in the augmentation block and only train these parameters so that you basically have those refinement vectors per label, again, trying to optimize the same kinds of triplet losses and thereby obtain your classifiers WJ. Okay. So that's how training for OAK is done. Now, inferencing for OAK is super simple. You start with the document, you pass it to the encoder, in our case, Distilbert encoder, right? And get the enhanced, get the encoder representation. In parallel, you also pass the document to the linker, which gives you top care relevant AKPs. You look up into your knowledge bank. You basically get those representations which have been trained over iterations, right? In the knowledge bank, and then you use the combiner C so as to combine the representation for X for the document with those AKP representations to get X hat. Now, your classifiers that you trained in the OAK fine-tuning stage, these WJs are going to be stored in an approximate nearest neighbor search index. So you basically take your X hat, query approximate nearest neighbor search index to get the nearest classifiers WJ. So that basically gives you the candidate labels. The final score F is basically computed as a fusion, basically a simple multiplication of similarity between X hat and YJ, and ANNS lookup score. So the similarity between 1 and 2, and of course the similarity between 1 and 4 in that sense. So the similarity between the encoder similarity and the classifier similarity. Okay, multiply those. Okay. Of course, at the end, you're going to return those labels which have high final score. Okay, so how do the results look like? So, this table basically shows you results over 4 different benchmark extreme classification data sets compared across several existing state-of-the-art extreme classification methods. What you also see are 5 different metrics: precision at 1, precision at 5, NDCG at 1, PSP at 1, and PSP at 5, which are standard metrics in extreme classification literature. So, of course, what you observe here is that our method OAK offers higher P at 1 on standard extreme classification benchmark datasets, all of them, more or less, right? So basically, it is about 2% better in terms of P at 1, precision at 1, with respect to NCAME, which is essentially the state-of-the-art method. Compared to graph-based methods like GraphFormer, OAK actually demonstrates much higher gains. For example, it's like about 15 to 20% higher inaccuracy, and compared to graph sage, which is the other GNN method, it's basically 5 to 7% higher P81 across all of these data sets. Okay. Now, we can also compare OAK with the ANSI, and this is basically comparison on ORCA's data set for retrieval. So ORCA's 800K data set, and as you observe, compared to the standard state-of-the-art retrieval ANSI method, we basically observe that OAK outperforms that one as well with 5% accuracy, with 5% precision at one. Okay. Now, we perform several ablations. So there are several components in the system, and we perform several ablations. For example, what if we do not use any auxiliary knowledge bank, no metadata, no auxiliary information at all. Okay. So, and here are ablations shown for two data sets. You observe clearly that, OAK with knowledge bank is better than OAK without knowledge bank, right? In most cases. Another ablation is for combiner. So what if you basically used mean pooling rather than you doing cross attention? So in a combiner, we actually do cross attention, although I did not talk about it in detail. It's basically just cross attention where one of those sides is basically your document representation, and the other side is basically the auxiliary knowledge representations, right? Auxiliary knowledge piece representations. Okay. So what if you just did mean pooling? So as you observe, cross attention is super important compared to mean pooling, right? So cross attention is super important compared to mean pooling. We also have two triplet losses and an MI calibration loss. So three losses to pre-train our method. So we did ablations to basically just say that, hey, what if we basically just did triplet loss with respect to the enhanced representation and ignored the encoder regularization or this calibration, right? And both of them seem to be adding value across metrics and across both of these data sets. Of course, more results on the paper, more details over other data sets and so on. So lastly, we did an ablation for early concatenation versus late attention fusion. Remember, you could basically just do some kind of retrieval augmentation and do early string-based concatenation. We observe that concatenation in the embedding space gives you better results because you could actually learn better representations for those auxiliary knowledge pieces separately in the knowledge bank rather than combining them as strings in the input itself. Okay. Now, we also try to observe the performance on tail. So typically in extreme classification, good performance on tail is difficult to achieve. Tail, so what do I mean by tail? Those documents which are associated with very few labels, or those labels which are associated with very few documents. Okay. So what you see is two plots, so document quantiles and label quantiles. So what this basically means is that, you have about 84K documents here and you have 8K documents here. So this is the head quantile, this is the tail quantile. Okay. Similarly, these are the head labels, these are the tail labels, and of course, this is the complete result. Okay. There are comparisons between OAK, Endgame, and GraphFormer on P8 precision at 5 metric. Okay. On this particular data set. Okay. And what you observe here is that OAK consistently outperforms Endgame and GraphFormer, both of those methods, the best GNN method and the best state-of-the-art extreme classification method, and is able to predict precisely for rare documents as well as for rare labels, right? So the precision for rare documents and rare labels is also pretty good. Okay. Now, basically at runtime, we use our prediction linker, right? We use an extreme classification based linker to link the relevant the relevant AKPs within the input document. Okay, what if we basically used Oracle or ground truth auxiliary knowledge pieces? Okay, so you see, these are the results with predicted auxiliary knowledge piece, and these are the results with Oracle. Okay, these are the results with Oracle auxiliary knowledge pieces. So what do you observe? So 33.71 on WikiC also titles becomes 38.92. Okay, so the idea is that if you really look at these numbers, you'll observe that these numbers are much higher than those numbers, which basically means that if we can improve our linker even more, there is hope that our method can actually result into even better results, right? So, however, this really holds only for short text data sets. Only for short text data sets, results are better when using ground truth AKPs. Okay, but consider long text data sets or full text data sets like Wikipedia 500K. Now, if you look at this, sometimes if you really compare, for example, this, you actually get better results with the ground truth, but many times, your prediction-based results are actually better. Many times, your prediction-based results are actually better. Okay. This basically just says that for full text data sets, your trained linker quality is actually better than for short text data sets, and therefore, you may not achieve a whole bunch of gains if you basically just end up using the ground truth Oracle linkages. Okay. Okay, so we also ran this on Bing sponsored search, ads kind of use case. So the idea is to match queries to billions of bid key phrases. That's why it's an extreme classification problem. You take queries and you want to map it to bid key phrases. Okay, we used web pages clicked as auxiliary data. So for those queries, we also know from search, what web pages were clicked. So we use that as additional, auxiliary information. Okay. Here are some offline results. So we compare OAK with 3 proprietary methods. For proprietary reasons, we can't really talk about those methods in detail, but they are actually implementations of popular dense retrieval algorithms, right? And as you observe, OAK really leads to way better results compared to those existing algorithms that are running in Bing production at this point of time in sponsored search. Okay. We also did comparisons by running our system online. So we actually deployed the system online, did some flights, as we call them, or A/B tests. And on A/B tests, basically, we compared the accuracy of OAK on top of the existing production system with these 4 metrics. Click-through rate, so how many times an ad was clicked compared to how many times it was shown. Impression yield and click yield, which basically is number of ad impressions and clicks per user query search. Okay. And then lastly, keyword density, which is a fraction of predicted keywords passing the relevance filters, passing the final filter so that they make sense. Okay. We observed that the click-through rate actually increases by 0.84% and the keyword density increases to 0.7%. Of course, this basically means revenue gains for Bing ads in that senses. Okay. Or broadly Microsoft ads in that senses. Okay. If you look at the yield gains, CY and IY, again, you observe that across different query quantiles, we do observe significant increases. This is percentage yield gain, significant increases compared to the standard production system that we have. Okay, here are sample predictions from OAK, in-game, and Graph-Former, the best state-of-the-art extreme classification method and the best method, GNN-based best method. Okay, look at some documents. So let's take some river, right? So this is some river, West Nakdong River. Okay, so these are the predicted extreme classification, predicted auxiliary knowledge pieces. And this is a list of ground truth labels. Okay, so essentially, the ground truth labels are of course good. Clearly coming from Wikipedia in that sense. So this is basically a Wikipedia use case where the idea is essentially, you have the input document and you want to sort of predict, I think in this case, other relevant. So you have to predict the categories. You have to predict the categories. Okay. So, and the auxiliary knowledge pieces are essentially see also titles. Okay. So what you observe is that, ground truth labels are great. Our labels are also not bad. Our auxiliary knowledge pieces are not bad. Okay. Sorry, these are auxiliary knowledge pieces. These are ground truth labels. So these are essentially categories. So these are ground truth labels. And what we observe is that these are the OAK predictions. And if you compare, Nakdong River matches. Okay. List of rivers in Asia matches. List of Korean related topics matches. Geography of South Korea matches. Only one incorrect result that we have, right? Han River, right? If you look at endgame predictions or graph form predictions, several incorrect results, okay? Several incorrect results compared to the ground truth, okay? And all of this is thanks to those awesome predicted auxiliary knowledge information that we got thanks to our linker and then the nice combination that OAK does on top of it. Okay. So in summary, in this paper, I basically discussed how you could use auxiliary knowledge pieces or auxiliary information for diverse and accurate extreme classification. We propose a modular OAK architecture, which does joint training of auxiliary knowledge pieces, piece representations on top of any encoder for that matter. It's modular in nature. Right? This involves 3-stage training scheme, linker training, OAK training, and also OAK fine-tune. We also involve, of course, encoder regularization and mutual information-based calibration loss. We observed state-of-the-art results on several extreme classification tasks, including ad keyword prediction, Wikipedia categories and see also prediction, and web page prediction. Lastly, what is super important is that OAK's inference takes less than 10 milliseconds, enabling it to be deployed